Good afternoon. Today I'll present our work on real-time anomaly detection for downhole tool failures using HAI. Downhole failures are a major case of non-productive time in drilling, costing millions per rig annually. Traditional reactive maintenance isn't enough. We have built a hybrid HAI framework that detects pre-failure anomalies from 15 to 30 seconds in advance, achieving 92 precisions and cutting false alarms by 65% compared to conventional methods. The system runs entirely on rig side hardware with sub 30 milliseconds latency and doesn't rely on cloud connectivity. Downhole tools operate under extreme conditions: high loads, abrasion, severe vibration, and heat. Common failures include bit wear, bearing failure, stuck pipe, and motor stalls. These carry heavy consequences. Unplanned trips account for 10 to 12 or 20 of rig time, costing millions per rig per day, per year. Beyond direct costs, sudden failures can cause blowout or well abandonment. In critical water regions like Kazakhstan's Mangistau Peninsula, any downtime directly worsens water storages. Despite the high stakes, most operations still use reactive maintenance. Fixed threshold alarms generate too many false alarms because normal drilling through hard formations can exceed an unfixed limit. More importantly, they miss precursor patterns that develop across multiple parameters. Isolation forests and one-class SVMs read each window independently and ignore temporal dependencies. Cloud-based AI adds from 5 to 20 seconds of latency, often exceeding our prediction window, and fails during network outages. In remote deserts of offshore sites, this is unacceptable. Reactive alarms only sound after irreversible damage has already occurred. Our solution is a hybrid edge AI framework. By running models directly on rig hardware, we remove the dependency on cloud connectivity essential for remote desert, offshore, and other locations. With unstable satellite links, HAI enables milliseconds latency supporting real-time closed-loop advisory systems. This represents a real shift from reactive to predictive maintenance, from cloud to edge processing, and from batch to real-time streaming. Our hybrid design balances the sensitivity of unsupervised learning with precision of supervised validation. We formalize the problem as follows. We monitor 8 sensor signals: weight on beat, rotary speed, surface torque, triaxial vibration, flow rate, and standby pressure, all at 10 Hz. Our goal is to detect immediate irreversible damage within the next from 5 to 30 seconds, enough time for proactive intervention. The low bound ensures the warning is actionable. The upper bound limits us to a physically meaningful window, beyond which precursors become indistinguishable from normal variability. We learn a mapping from recent sliding windows to a binary decision under strict real-time constraints. Several key challenges exist. First, extreme class imbalance. Failures occur less than 1% of the time. Standard classifiers achieve higher accuracy by simply predicting normal, missing critical events. Second, noise and non-stationary. Formation changes cause systematic shifts even with healthy tools. Third, strict timing. We need decision within 50 milliseconds, making deep networks infeasible without optimization. Fourth, interpretability. Operators won't act without understanding why an alarm was triggered. Our architecture has two stages. Stage 1 is an unsupervised LSTM autoencoder that learns normal drilling dynamics. It computes a reconstruction error, low for normal patterns, high for anomalies, and uses an adaptive threshold to generate flags. Stage 2 is a supervised light GBM classifier that validates these flagged anomalies using a rich feature set, including statistical summaries, reconstruction errors, and spectral characteristics. This hybrid approach is novel. The autoencoder provides sensitivity without labeled data, while the classifier filters false alarms. The autoencoder has a symmetrical design. The encoder compresses 60 to 8 inputs through LSTM layers down to an 8-unit bottleneck, forcing a compact representation of normal behavior. The decoder reconstructs the original sequences. It's trained exclusively on normal windows using mean-squared error. For inference, reconstruction error acts as the anomaly score, rather than a fixed threshold. We use an adaptive one based on the rolling median and median absolute deviation over the last 100 seconds. This automatically adjusts to changing baseline error during formation transitions. For every flagged window, we extract a rich feature vector. Statistical summaries capture each sensor's distribution. Reconstruction features includes overall and per-sensor errors. Spectral characteristics from FFT are especially important for bearing-related detection. The classifier is trained with smooth NN to handle class imbalance. It synthesizes new minority samples and removes ambiguous instances. We optimize hyperparameters through cross-validation and prune features with importance below 0.01, removing 12 features to speed up inference. We use field data from 12 wells in Kazakhstan, 7 uranium in situ recovery wells, and 5 water supply boreholes in Mangostau Peninsula. In total, we recorded 625 hours of active drilling, producing 22 million raw samples at 10 Hz. After sampling to 5 Hz and segmenting into 12-second windows, we obtained 200,000 labeled instances. We identified 42 distinct failure events, bit wear, bearing failures, stack pipe, and motor stalls, confirmed by post-run inspection. Only 1,200 windows, or 0.68% correspond to pre-failure states. This survey 115 to 1 imbalance justifies our use of smooth ANN. A field case shows its practical value. At the uranium well at 487 meters depth, the autoencoder showed a progressive 35-second rise in reconstruction error. The light GBM confirmed an anomaly 18 seconds before the torque U signal collapsed. Acting on this, the driller reduced weight and pulled out, revealing a fractured bearing race that would have seized within seconds. This prevented a fishing operation, saving an estimated $45,000. SIAP analysis showed torque standard deviation and vibration spectral centroid as the most influential features. Per sensor reconstruction error highlighted which sensor deviated most. Combined high errors on vibration and torque strongly indicate a downhole mechanical issue. Operators reported this explanation increased their confidence and counter sports time by 40%. The system is retrofittable with minimal hardware and NVIDIA Nano running on the 15 watts and uses existing sensor suites. Estimated benefits includes a 35% reduction in non-productive time, saving hundreds of thousands of dollars per rig annually. The averted fishing operation saves $45,000. Allowed fatigue is virtually eliminated. More important, the system enhances safety by preventing future failures that could escalate into blowout or uncontrolled fluid releases. For water supply wells in arid regions like Mangistau, this means more reliable access to water. To conclude, we have presented a hybrid Edge AI framework combining an unsupervised LSTM and autoencoder with a supervised light GBM classifier for real-time failure detection. Validated on real field data from 12 wells, it achieves an F1 score of 0.90, a 50% improvement over the host, with 24-second lead times and just 2 false alarms per 10 hours. The 28 milliseconds latency ensures reliable performance without network connectivity. We acknowledge limitations. Only 42 failure events mean some types are underrepresented. Future work includes multi-well transfer learning, integration with automatic drilling controls, semi-supervised adaptation, and federated learning for privacy-preserving updates. We also plan to extend this to geothermal and mining applications. Overall, this work shows that the edge-enabled predictive maintenance can generally shift drilling from reactive to proactive failure management, improving safety, cutting costs, and strengthening critical energy and water infrastructure. Thank you.